Hello everybody, this is Carol Bouchard, and this is Coefficient of Inbreeding Bootcamp, which I'm teaching together with Dr. Peter Olliuk in the Netherlands. Today we're going to talk a little bit about how to calculate the coefficient of inbreeding. And although you're never going to have to do this yourself because most pedigree software will do it for you, it's important to know how it's calculated because that will help you understand what it means. So if we go back to the definition of inbreeding that we got from Dr. Olliuk last time, we saw that the probability, inbreeding is the probability that both alleles at a locus are identical by descent. And by identical by descent, we mean that the alleles are identical because they were inherited from the same ancestor. Let's look at this pedigree of a whippet, and you can see that back here, this sire and dam appear twice. And these are great-great-grandparents of this dog right here. So this animal is inbred in this generation, and these two individuals here and here, Golden Kate and Blue Carrie, are full siblings. So let's say we want to figure out how inbred animal X is here. So we're going to simplify this pedigree by putting letters for the animals in here and then redrawing it with circles and sticks. Circles represent the females, the square boxes represent the males, and each letter here corresponds to the letter here. So you'll see we have G and H that are shared on both sides of the pedigree of X, which appear here and here, and we write them right here. And D and F, the full siblings that appear in this pedigree, are here, F and D. And then we have the parents of the dog we're interested in, and this is X, the dog. So here's the stick diagram we just drew, and we're going to simplify it even a little bit more. There are two individuals here we don't even need to worry about, and that's C and E. So we're going to get rid of them, and then we're going to redraw the connections between the dogs by representing them as the path an allele would take from one animal to the next. G here is the parent of F and could have passed an allele here and here. And likewise, D would pass an allele to H, and A would have passed an allele to X. So these are called paths. We know that X is inbred. Here is where the inbreeding is. So the question we want to ask is, what is the coefficient of inbreeding of X? What's the probability that X has inherited two copies of the same allele from an ancestor? Let's start with a simple example. Here's a sire and dam, and there are 4 different alleles for the gene T. How likely is it that this animal X will inherit a particular allele? First, let's draw the diagram to show the paths of inheritance as we did before. And then we have this. We want to know the probability that a particular allele, say the A allele of the T gene, gets passed to X. And we know that there are 2 alleles at every gene, at every locus, and the probability of one or the other of them getting passed to an offspring is equal. Which one goes is completely random, at least in theory, and the probabilities are equal. It's 50-50. So the probability that TA will be inherited by X is 0.5, 50%, and it's exactly the same as the probability of inheriting the other allele. And likewise, on the sire's side of the pedigree, the probability of either of these alleles being inherited by X is 50%. Now, if we look at the whippet pedigree again, we can see that an allele can be passed from H to X 2 ways. Once through F, and once through the sibling D, this way. So I've redrawn these paths separately so they're clear. One of them is H. This one here is H to F to B to X, and alternatively, that allele could go from H to D to A to X. And to figure out the probabilities associated with this, we have to ask, how many individuals are there in the path between H and X? And for both, it's 3. We know that the probability of inheriting a specific allele is 0.5, and it's 0.5 for each of these steps. So to compute the probability that X will inherit a specific allele from a great-great-grandparent, we multiply each of these probabilities here, 0.5, 0.5, 0.5, which comes to 0.125 or 12.5%. So that's the probability of inheriting one allele, either TA or TB, from the ancestor X by this path. So what's the probability of inheriting two copies of the same allele from H, one of which is inherited through the ancestor F and one that's inherited through the ancestor D? To figure this out, we're going to trace a loop from the dog that we're interested in through the common ancestor in the pedigree, which in this case is H, and back down to this animal, and count the number of animals in that path, in that loop. And then we count the number of animals in that loop, which is 5. So like before, we calculate the probabilities for each step, which is 0.5, and we come up with 3.125, which is the probability that X will be homozygous for TA. And those of you who know some mathematics will see that you could also write this as 0.5 to the 5th power, because it's 0.5 multiplied by itself 5 times. And of course, you get the same answer, 0.03125 or 3.125%. Okay, we have actually two shared ancestors, both H and G, in X's pedigree. So what's the probability that X could be homozygous for an allele that came originally from ancestor G? To figure this out, we do exactly what we did for H. We identify the loop through G from X and back again, and count the number of animals, which is 5. So here we have these two shared animals in the pedigree, and this is the inbreeding that we've calculated for H, and the inbreeding associated with the presence of G in this pedigree. And to calculate the total coefficient of inbreeding of this animal, its total inbreeding, it's the sum of these two probabilities, in which case it's 6.25%. What we've just calculated here is something called Wright's coefficient of inbreeding, which he labeled with the letter F. So you might see it written sometimes this way, F equals n some percentage, or more commonly the dog people will write COI or CI, short for coefficient of inbreeding, and then this percentage. Let's go back to the definition of inbreeding that we used at the beginning, which is a probability that X will be homozygous for two alleles that are identical by descent. And for this particular example, that probability is 6.25%. Okay, finally, I want to just emphasize a few points that are important for you to remember. First of all, the coefficient of inbreeding doesn't tell you anything about which genes will be homozygous. They can be good genes, they can be bad genes. You don't have any way to know. Second of all, it doesn't tell you whether the effects of inbreeding will be good or bad. And finally, it doesn't tell you whether an animal will be diseased or healthy. An animal with a high coefficient of inbreeding can be healthy. An animal with a low coefficient of inbreeding could have a whole raft of health problems. Coefficient of inbreeding is simply a prediction. It's a statistical probability, like the chance of it raining tomorrow afternoon, or the chance that you'll get heads the next time you flip a coin. Coefficient of inbreeding is a probability of homozygosity in an animal. If the homozygosity happens to be for a desirable gene, then coefficient of inbreeding is a measure of potential benefit. So that's good. On the other hand, if the homozygosity happens to be for an undesirable gene, the coefficient of inbreeding is a measure of potential risk. And of course, like we see up here, you have no way to know whether inbreeding will produce good things or bad things. So here are some things we're going to talk about next time. First of all, how many generations of pedigree data do you really need to use when you do these calculations? Second of all, what happens if there's missing data, which quite frequently is the case? What about where the inbreeding occurs in a pedigree? Is recent inbreeding better or worse? than old inbreeding. And finally, we'll talk a little bit more about the consequences of inbreeding, both good and bad. I'll see you next time.